Sollten wir Leute, sorry.
Thank you. Yes, so I will tell about our combined theoretical and experimental efforts on the way to reach ultracold quantum regime in ion atom systems, because during the last 2 days we have heard that there are lots of efforts, but still we are in relatively warm collision regime. So I will try to discuss like 2 possible ways to somehow reach the few or even single partial wave regime. So, I mean, it was already justified why this field is so interesting and exciting, but I will just repeat that like we want to combine ultracold atoms, and ultracold atoms are great systems because we can have relatively large number of atoms, we can have relatively long coherence time for these systems. They are still very fully controllable, and what is the most interesting, they are fully quantum matter. Then, on the other hand, we have the trapped ions. Then they are much smaller systems. The number of ions that can be trapped is smaller, but they are strongly interacting. And because they are strongly interacting, so then the time, the operational times are slower. They are faster in operations. Then they are fully controllable. And what is also interesting in the context, what was told by Tommaso Calarco or Antonio, that probably trapped ions are much easier to transfer to technology than cold atoms, so they can be the kind of gate to technological applications. And in our community, we want to combine these ions with atoms in one hybrid systems, and hopefully all the nice features of these 2 systems on their own will be inherited, and also some new emerging features will be there, and these 2 systems will be coupled by relatively strong ion-atom interactions. And there are many applications that were discussed during this workshop, but for me, because I'm partially chemist, so cold control chemistry is very interesting, but also precision measurements, and a lot of applications, possible applications in quantum simulation, computation, and sensing can also come. And from the perspective of the first part of my talk, especially the simulations, quantum simulations of solid-state physics will be interesting. So these are the plots from 2 proposals, where in one of them the emulation of solid-state physics with the linear chain of heavy ytterbium ions in a trap surrounded by fermionic atoms was presented. And the idea is that it was shown in this paper that in this kind of arrangement, the fermions around these heavy ions can form kind of band structure, and they can be used to simulate the properties of real materials. And although there were some proposals on Josephson junction, but because the experimental group of René Geritsma is on the way to realize this will be the most important justification for the first part of my work. But as it was already pointed by a few people, especially Ronnie Ozeri, that we have always micromotion in the trap. So even if we have like excellent setup when we can correct it to 200 micro Kelvin, still it is there. So it can be the problem. So then of course it would be the best to use the system that is the most suitable. And there were few proposals where people investigated what systems are the best for this. And it happens that most probably the systems where the mass ratio of the ion to the atom is the largest. So then one of the most heavy ions that we can have is ytterbium. The lightest atom that we can have at ultra-cold temperatures is lithium. So it suggests that ytterbium ion plus lithium atoms can be one of the systems where we can be the closest to the S-wave regime with correcting having the best micromotion correction and so on. But also there is the other problem that once we have ion atom systems, usually there is quite complicated chemistry or dynamics at short range. So we can have several processes, like we can have non-radiative charge transfer when the charge is transferred by some couplings between electronic states at short range. We can have radiative charge transfer. We can have also radiative association to the ground state. And all this has to be included. And in fact, because all this happens at short range, so the approaches which use only the the asymptotic description. Anyway, they usually need some input about specific couplings from on the short range, in contrast to other systems, but sometimes only the universal probabilities of the systems can be calculated from only the long range part of the dynamics. So there are a few challenges like including or avoiding radiative charge, non-radiative or radiative charge transfers and association losses. So we still would like to have control over ion-atom interactions. So it was presented that by controlling the spin, we can have some control. And of course, one of the best solutions would be to access the Feshbach resonances that are so commonly used in the cold atom community. But to do this, we have to really go to the few or even single S-wave partial regime, and we are still far away. And also, we have also always deal with the micromotion if we use pole trap. So then maybe the idea is to use something else. Okay, so in this plot we combined the experiments that were realized. I hope I didn't miss any in the cold regime. So we can see that still the lowest temperatures that are achieved are around millikelvin. And then we also plotted here the position of the characteristic energy scale defined by this expression for the ion atom systems, and it can be compared to the highest of the p-wave barrier. So what we can see that we are even in the best cases, like for the systems with the smallest reduced mass, we are at least 2 orders of magnitude from the S-wave regime. And for most of the systems, we are 5 or 6 orders of magnitude. So it's rather a huge gap that, of course, all people here are trying to skip, but there is huge gap. So of course, among these systems, probably the best, if we want really to go to few partial waves, is to choose the system where we are the closest to the quantum regime, to the single partial or few partial wave regime. And then the best would be to use the systems with the smallest reduced mass. So the smallest reduced mass will be for systems containing lithium atoms, like ytterbium plus lithium or calcium ions plus lithium. Or the other solutions to be avoid pole trap and go directly to ultracold regimes. And so in the first part of my talk, I will present the efforts on the systems of ytterbium plus ion and lithium atom, which I investigated theoretically a few years ago, and recently René Gerritsma at University of Amsterdam is pushing towards realization, and the first results have been obtained. And in the second part, I will present the new proposal where we want to access directly the ion atom scattering in the ultracold regime by using the Rydberg molecules, where we specifically to have the S-wave regime at as high temperature as possible, we use the gas of lithium atoms, because this will. But presenting this table, I will take a moment to make a small advertisement that. Together with Paul Julien, Zbyszek Idziaszek, Tomaso Kolarko, Antonio Negretti, René Gerritsma, and Krzysztof Jakimski, we prepared a review article about the systems, because we found that, like already 1 or 2 years ago, we found that some kind of complete and broad review that would be accessible both for PhD students and who include all the works is missing. So we prepared this, and because most of people here has lots of contributions, so I would like probably next weekend, at the beginning of the next week, to send this like PDF and to ask to check, for example, if we correctly, first of all, if we included all important or all your works, or if we cite and describe them correctly, because of course, before we put it on archive, we would be sure that we don't miss any important work, or we didn't forgot to mention some great works. Okay, so now moving back to the research. So the first part will be devoted to the theoretical description and first experimental results for the ytterbium ion plus lithium system. And in the second part, I will go to our new proposal which is under construction in the Tillman-Faust group. Okay, so as I mentioned, this system has one of the smallest reduced mass that can be imagined for ion atom systems among the combination that we have now accessible in experiments. And for these reasons, we should be the closest to the single partial wave and quantum regime, when we can hope to observe some resonances and maybe even the Feshbach resonances to control ion atom interactions. Then this work, theoretical part, the first theoretical part was realized with Christiane Koch and Robert Moszyński, who were my PhD advisors, and then the next part and calculations for more excited states were realized recently with the group of René Geritsma at Amsterdam. Okay, so this is the structure of the lithium-ytterbium ion. So the system, when you have these two atoms and it's ionized, the entrance channel here is quite well separated from other thresholds. So this suggests at the beginning that this system should be relatively immune against radiative or non-radiative change transfers, because there is no direct coupling between these entrance channels with other electronic states. So there will be no not radiative losses, and at the same time, the energy release in this transition is relatively small, so it also helps that the radiative losses and radiative association to the ground state should be relatively small. Yes, and for the lowest excited state, we were able to calculate quite accurately this potential energy curves using methods of quantum chemistry. We calculated the transition electric dipole moments, and where it's very important to remember that transition dipole moment between the entrance channel and exit channel, where we have charge transfer, is strictly vanishing at large internuclear distances. So any transition up or down, they are strictly forbidden at large distances. So it's not it should not be mixed with the, for example, intercombination line transitions where the dipole transition is forbidden, but still we have small admixtures at even infinitely large distances, and the physics is a bit different. So there are this transition dipole moment that vanish exponentially because of the symmetry of charge transfer. And of course, there are some asymptotes, some excited states that have the same arrangement of charges, and then of course the transition dipole moment asymptotically is allowed because it approaches the transition dipole moment in the ion or atom respectively. So in this system, as I mentioned, we can have spontaneous radiative charge transfer or radiative association. There are two first usually to be considered in this kind of systems. But of course, to know if the charge transfer or radiative losses are problematic or no, we should have some estimations of the elastic collisions, because once the elastic collisions are much larger than any lossless collisions, then probably we have still enough time to realize our quantum simulation or computation application without being worried about losing our ions or some decoherence processes. So these are the rates for elastic scattering, and we see that in the millikelvin regime, independent of the state or the reduced mass, they took the value around 10 to minus 8 centimeters square per second. And this has to be compared to the radiative charge transfer losses. And this plot shows the radiative charge transfer losses calculated for this system. So for two isotopes, so we didn't scan in this picture systematically the scattering length. We just took two systems with relatively different scattering length. And we see, first of all, that of course the behavior is typical for the Langevin capture dynamics. Then at some temperatures of several to 100 millikelvins, there are some shape resonance. If we look on the scattering, or if we look on the rates with the energy in the rate for the given energy, but of course in the system we have thermal distribution, so we have to take average over these calculations, and then this dashed line shows the rates that can be expected in experiments, so they are quite well averaged. So in this system we don't rather expect any shape resonances to be measurable at any temperatures. But then what is also quite important and interesting and typical for most of the ion atom systems that are used, that when we decompose the total rate for radiative charge transfer or radiative charge losses, that the contribution from the radiative charge transfer, when the charge is only transferred and the atoms are still free, they don't form bound molecules, is much smaller. So it, in fact, most of the losses in this kind of collisions leads to the formation, to the association of the molecules, or at least this is what we expect from our calculations. But as I mentioned, because it's impossible for systems larger than, let's say, 5-6 electron systems to calculate from first principles scattering lengths. So I believe that always any scattering calculation should be cross-checked with the possibility that the scattering lengths are different. So to do this, one of the approaches can be to scale simply the full interaction potentials, because by scaling potentials we change the scattering length. So we did it for our system in the range which correspond to more or less the appearance of one additional bound state. So we scale the full range of the scattering lengths. And we see, and the results are presented for two temperatures, for 1 millikelvin and for 10 microkelvin, where 10 microkelvin should be the temperature where we expect already just few partial waves. And we see that there is some dependence. There are some resonances once the bound states appear in the system, once they cross the threshold. But when we look on the ratio, we see that in fact for most of the possible scattering lengths, the ratio is quite large. So it means that this system is very favorable in the context of the ratio of elastic to inelastic collisions. So we have to be really unlucky to have the scattering length that correspond really to this dip somewhere there. So yeah, we can be unlucky, but then we can change the isotope and then the position of the bound states for different reduced masses are different, and then we never be for two different or few different isotopic mixtures at the same position of this curve. So this system is quite quite optimistic when we think about the losses that can be problematic. But because I like molecules, so it's also interesting for me to see what kind of molecules are produced in this kind of association collisions. And this is the composition of this is like the state-dependent rates for the formation of molecules in the ground, of molecular ions in the ground state versus different binding energy. And we see that the most probably is the formation of the molecular ions with binding energy around 1,200 wave numbers, and this is again quite typical for all the ion atom system that we have now in our experiments, that because the transition dipole moment decay exponentially with the intermolecular distance, then the transition probability to the most weakly bound state is really suppressed. So it's really in contrast to what is observed in the photoassociation experiments with neutral atoms, where usually we have access only to weakly or relatively weakly bound state. Here, the most probable is the formation of deeply bound states. And also, I compared in this plot the formation rates for two different temperatures. So for 100 nanokelvins, that is of course completely out of reach now and probably for many years, but maybe I hope to be wrong. And then we have only single partial regime, so we produce molecules only in the P wave because we have collision in the S wave. But once we are at that temperature of 10 microkelvin, it's the temperature where we have already mixture of S and P wave collisions. Then we produce molecular ions in four different partial or three different partial waves, in fact, because the fourth is negligible to show that we have like really these two partial waves in the collision and then three possible partial waves as the output. Okay, but so once we have this, we can see that the rates for this individual transitions are relatively small, and they are also much smaller than the rates for the elastic collisions. So we can hope that we can maybe by applying laser field to induce. So you can think about or photoassociation to the excited state or kind of photoassociation to the ground state, or it's more properly to tell about this like stabilization to some selected bound states in the ground state potential. And by applying laser field, we can hope that we can drive and form the molecular ions in selected vibrational state. And this is the spectrum for the photoassociation for some reasonably chosen intensity of the laser field. And we can see two most important features. First of all, the shape of this spectrum is very similar to the shape of the spontaneous radiation for association, because both this transition and the spontaneous radiative association, they are governed by the same Frank-Condon factors and vibration and transition dipole moments. So it's not surprising. And also we can see that the rates here are around 2 orders of magnitude larger than the rates for the spontaneous radiative association. So we can really hope that we can selectively address the formation of the molecular ions in some selected levels. We can also think about that's typical photoassociation going to some excited states, but it's not, again, typical as in any neutral systems because the dipole moment vanish with the distance really strictly. And then we have, again, the spectrum is very similar. So, again, the probability of formation of the relatively deeply bound or the states, the levels from the middle of the wall is the largest. And then the formation of the most weakly bound molecular levels is really suppressed because there is no transition electric dipole moment at the large internuclear distances because of the strict suppression of it. Okay, so once we investigated the impact of the laser field, we also looked on the impact of the magnetic field. So it's because we would like really to have the control of the scattering lengths of the ion atom systems, and one of the possibilities to use Feshbach resonances. So these are some example plots for the different isotopic mixtures of the ytterbium ions and lithium atoms for few temperatures. So of course, in the ultracold regime at 100 nanokelvins, the resonances are really very well pronounced. Then once we go to larger temperatures, we see that already at 10 microkelvins, the resonances are much less pronounced. So please note that the scales are completely different. So here we have many orders of magnitude. Here we have 2 orders of magnitude, or even 1 order of magnitude, and here we have linear scale. So once at 100 nanokelvins, of course, the resonances will be very pronounced. At 10 microkelvins, we can still hope to see something, but of course, at 1 millikelvin, this will be completely negligible, especially that this result don't include yet thermal averaging. So thermal averaging for 1 millikelvin completely wash it. But this is for the elastic scattering. But once we look at radiative losses, we can see something a bit different. So the resonances are a bit more pronounced once we go to larger temperatures. And the reason for this is because the radiative losses, they are governed not by the reflection or scattering from the centrifugal barrier, that is what we have for elastic scattering. And then just for the larger partial waves, we have scattering from the barrier, and then we have more and more contribution to the elastic scattering from the centrifugal barrier. For radiative losses, any losses that are governed by the short range part, and this is short range physics. So for these processes, we need tunneling of the scattering wave function to short range to have losses. So then really the resonances will be there because there is no contribution from higher partial waves to this process. Okay, so now these were the results that we presented 2 years ago, and now there will be the new results of the experiment in Amsterdam that was realized. They were realized by René Geritsma. So he built the system, and he have the ytterbium ions in the pole trap with the fermionic lithium atoms in the mod. And in the future, he will put it to the dipole trap. So first, as a check that the system works and we understand what is going on inside, he investigated the charge exchange, charge transfer process, depending on the collision energy, depending on the isotope, and depending on the electronic state. So here are the example results versus energy for 2 different isotopes and 2 different states, like P 1/2 and D 3/2. States. So we can see that there is they are independent on energy. So this confirms that yes, we are in the Langevin regime. They are also relatively they don't depend visibly on the isotope, but they depend strongly on the electronic state of the ytterbium ion. So once we put this in the table, we can see that yes. So for the ground state, it was in this system the density of ion atoms is not enough to have the accurate values of the loss rate. So there are only estimation of the maximum possible, and to have the proper because it's not possible to distinguish these losses from some background losses. But for the excited states, we have measurements, and we can see that for 2 states, for P and F states, the radiative loss, the exchange loss, charge exchange losses are really huge, like half of the classical Langevin rate. collision, and for D state it's much, much smaller. And then, of course, the question is, can we explain it, and can we provide some theoretical explanation for this rate? So to do this, I tried to calculate the interaction curves for the excited states of the lithium-ytterbium system, and unfortunately, it's very heavy. It's very problematic system. It's heavy because the ytterbium is heavy, but it's also very heavy because it's complicated. So for the for the ground state, we have these curves from the previous calculation, and we are quite sure about accuracy. But unfortunately, once we go to higher and higher states, then we start to have excited state of the ytterbium ion and ytterbium atom, where the F shells start to be open. And this is the huge problem, because in the F shell in the ytterbium we have 14 electrons and 14 electrons on seven orbitals. Then combining these 14 electrons with the other electrons from lithium, and the need to put these electrons onto the orbitals of not only the ground valence, not only on the valence orbitals, but also on several excited state orbitals, we start to have this system that computationally is not treatable with the present ab initio codes. So this result, in fact, presents only the curves that are obtained in the non-relativistic approximation. So the spin orbit coupling is not yet included here. And also we didn't include excitation from the F shell in this picture. So we see that we have already this spaghetti regime but neglecting probably more than 50% of states that are there. And unfortunately, there is no really hope to calculate these curves enough accurately to do the full calculation. So for the explanation of this, it's rather possible. I think we are now aiming to build some effective models similar to what was presented yesterday by the results from Svetlana group. But still, we hope to gain some at least intuition and qualitative explanation. And yes, and we can have some. Okay, so because maybe before I will go to this explanation, I would like to tell what are the biggest problems in the system. So when we have the many electrons strongly correlated, so we have two problems. So first of all, we have to include dynamic correlation. So this is typical, that is in all quantum many-body problems that has to be included. And this is for electrons. This is like in the classical way, it can be explained that electrons avoid each other and they know. So the mean field approximation does not include this. And we have to include that there are possible solutions to this. One of them is configuration interaction method. The other is coupled cluster method. And there are many other methods depending on the system. And then there is also the second problem that we have to include static correlation. And static correlation in our case is the part of the total energy that is coming from the fact that we cannot describe the reference state as a single reference, as a single state determinant state. So it means that we cannot use the methods that are based on the mean field solution based on the single state determinant. And unfortunately, once we include the many possible reference states, and then we want to combine it with many possible configuration needed to describe correctly dynamic correlation, we start to have billions of terms in our wave function, and it's too much for our classical computers. But to sum up, so the problem is that we have to include excitation from F shell in the ytterbium atoms. We have huge spin orbit coupling. We have large density of states. So these are a problem for us. But at the same time, the experimental results provided for this system, they are perfect for testing and benchmarking ab initio methods of electronic structure. Because now we have the system when we cannot really describe it correctly. So we have to use really the methods from the edge of the quantum chemistry. And hopefully, comparing the results provided by them can improve this method. But okay, so still, we aim to have some qualitative explanation of the observed rates, and to do this we looked on the spin orbit coupling and the nature of the states that surround the entrance channels. So we have that for these three states. For the F state, we have a really huge spin orbit coupling. The huge spin orbit coupling that corresponds to the splitting between the two F states of the order of 10,000 wave numbers is extremely huge. So it means that in fact the curves that in the non-relativistic pictures are somewhere they can be mixed with tens of other potentials. And for this state we have very small spin orbit coupling, or relatively small, of the order of only 1,500 wave numbers. And for P state we have mixed. So and somehow the order of spin orbit coupling agree with the observed rates. So that yes, in fact for F and P states we observe the largest charge transfer rates. For for the smallest. But there's also other part of this story. So once we look on the nature of the electronic configuration of the threshold surrounding the entrance channels corresponding to the ion with this state, we can see that when we have F state, when you have ion in the F state, then the thresholds of the other thresholds of the combination of ion atom and the other electronic state that surrounds the entrance electronic state, they have the same electronic configuration, and especially they have the same configuration of F-shell electrons. So it means that the charge transfer process involves only changing the position of one of the electron of the one electron orbitals, whereas for the D state, the configuration of F-shell electrons for the threshold that surround the threshold of the entrance threshold with the D state is of different nature. So we have completely different configuration of F orbitals because we have one of the electrons excited, and it means that the charge transfer process involves more than rearrangement of one electron. And in fact, when we ask about the couplings or non-adiabatic coupling between different curves with this, when there is difference of the configuration of F-shell electrons, we can see that the coupling is much different. So it means that the threshold in this case and this case, when the surrounding states are very, very similar, is very, very strong. But when we calculate the overlaps, the coupling between the states that have different F-shell configuration, then the coupling is very small. So there are these two possible configurations. So we have to distinguish what is true. Is it this spin orbit coupling or the nature of surrounding states, or maybe the resonant character of the entrance channel. But for this, we check that more or less for all these states, the position of the other states is similar. It's in the range of several hundred wave numbers. So rather the last explanation is not the one. But to do this, we look on the other results. So in fact, we look on the results from 2012 for the ytterbium ion and rubidium atoms. And we found that for this system, in fact, the order of the rates for the losses were opposite. So it means that in this experiment, the losses from the ytterbium ion in the D state was observed much larger than much larger, like order of magnitude larger than for F state. So it's opposite to our case. So explanation using the spin orbit coupling as an explanation is not true, because apparently we have different results and we have still the same spin orbit coupling for the ytterbium ion. But then once we look on the electronic state that surround these entrance channels here and here, we found that yes, in fact, the electronic configuration of the thresholds around the entrance channel containing the ion in these two states, they are opposite to ours. So it means that, again, in this case, if the ytterbium ions in this state, in this state where the losses were really strong, the entrance channel around this threshold, the thresholds around this entrance channel, they have the same configuration of F electrons, and at the same time, the couplings between them and the entrance channel are much larger, so it's really allow for really strong and fast non-radiative charge transfer, whereas for this state, in this case, it's opposite. And of course, the reason why it's this order is different for ytterbium plus rubidium and ytterbium plus lithium is because we have the curves, the energy levels of the ytterbium and of the rubidium and lithium a bit different. So this states here and this states here, they have a bit different orders. So finally, we found that not spin orbit coupling, but rather the couplings between the surrounding states, states surrounding the entrance channel as the crucial to explain the observed rates. And we are working on some more quantitative models, like including specifically different range of coupling between these states. Okay, I hope I have still time to talk about my second part. Okay, the second part is much shorter. So I will talk about using Rydberg molecules for the ion atom scattering, and this work is realized with the group of Tim and Pfau, where they are building the experiment. And first we did the calculation confirming that yes, it will work. So as we already have seen last days, that it's possible to have single Rydberg excitation in the BEC. So it's possible to have the single ion in the BEC with the electron somewhere far away. So in fact, if we looked at this system, it corresponds that yes, we have bound state, but we have really the ion plus atom and it's surrounded by these electrons. So in fact, inside the system, when we have Rydberg atom and many atoms around, or we have Rydberg molecule, we have inside the system this ion atom system. So why not to use this arrangement to probe really the ion atom scattering and ion atom collision? So this was the idea. Let's use the Rydberg molecule state, for example, something like this, to have the initial wave packet for the dynamics. Then let's ionize the Rydberg molecule, like throwing away the electron, and then looking what is going on for the ion atom scattering, where the initial state for this ion atom system is described by the wave packet that was before the vibrational bound state of the Rydberg molecule. And again, as I repeat this plot, so we were thinking about different systems. So first we decided that yes, we want the system that has the lowest mass, reduced mass, because we want to be as close as possible to the S-wave regime. And then we found that we have to use lithium atoms. So we checked several ions that we can use. So for both lithium and rubidium, and we found that first of all, it's what I present in the moment is quite universal. So we find it for several alkali Rydberg atoms in the system, and we decided that we will use lithium-lithium, as this is the best case that we can imagine. And this is the plot showing the arrangement of the system. So we have the potential, the Born-Oppenheimer potential for the Rydberg molecule. We have bound state corresponding to the Rydberg molecule somewhere there. And in this plot, I presented results for both lithium-7 and lithium-6, as the differences are not so large. So the Rydberg molecules look quite similar for these two states. This is logarithmic scale, so look that it's like a bit maybe strange. It looks a bit strange because it's logarithmic scale. Then we also looked at, okay, what is the rotational constant and what versus the line width of the transition. So yes, the rotational constant is larger than the typical line width for this transition. So we will be able to excite and produce really this bound state, this Rydberg molecules for the ionization. Then ionization process is rather straightforward. And then after ionization, this is our initial wave packet decomposed into the scattering state of the ion atom potential, or in fact, this is Fourier transfer of this wave packet. So we see that the most probable energy is quite close to this limit, to this S wave limit. So yes, we have some tail of the higher energy. So the average energy of the initial wave packet is like 2 or 3 times the S wave regime. But we are really close to this. And second, because we start, and I didn't mention that we decided to use the S wave Rydberg molecule. So in fact, we checked all numbers from S to F, and we found that in fact there is no advantage of using F or D or P state Rydberg molecules, and we use S wave molecules. And at the same time, because we start from S wave, so somehow by the symmetry of the system, we restrict our collision to be only in the S wave if we can have very good control over the possible electric fields that are around. Okay, so we have this initial wave packet. Then I also presented 2 bound state of the ion atom potential because lithium atom in the contrast to lithium ytterbium atom is very small system when we have only 5 electrons. And already for 4 electron system, the exact calculation of electronic structure are possible. And we tried to do this the same, and in fact, we think we are able to predict more or less with not so bad error bars the scattering length for the collision of lithium ion with lithium atoms, because again there are only 5 electrons and only 1 valence electron, and 2 bound states for the respectively lithium-6 and lithium-7 molecular ions are presented here. So once we ionize the Rydberg molecule wave packet, we project the wave packet onto the ion atom potential, and of course we project also partially on the bound states in the ion atom potential. So then we can look on the evolution. So in the experiment they will have time resolve imaging of the evolving wave packet. So we can hope that we can look on the evolution. So in this plot we presented the evolving wave packet for 2 different initial scattering length of the ion atom potential with the step every 50 nanoseconds. So every 50 nanoseconds up to 1 microsecond, and the initial wave packet is somewhere up here because it's much more peaked than the evolving wave packet. And what we can check that when we look on the position of the maximum of this evolving wave packet, in fact, it depends on the scattering length. It depends on the scattering length because part of the initial wave packet is projected onto the bound molecular state. So it means that the energy of the resulting part of the wave packet to have the same expectation value of the energy for the system must be different. So for this reason, the evolving wave packet has a different speed. And if we are able to observe the nodes of this propagating ion atom wave packet in the experiment, we are able to assign the scattering length for this potential. And we find that depending on the scattering length, we can use two methods. So if the scattering length is in the negative range, we can use the velocity, the propagation of the maximum of the wave packet as the indicator of the scattering length. Whereas if we are in the positive range of the scattering length, then we can look at the fraction of formed weakly bound molecular ions versus the scattering length, because we have this kind of dependence where for some range of the scattering length, up to 50% of the initial wave packet is projected directly to the molecular bound state, and depending on the scattering length, it can be a bit different. But once we go for scattering length smaller than 0, then almost nothing is projected to the bound state, so then we have to use this second approach with the observing velocity. So in this way, we propose two methods of measuring the ion atom scattering length in this kind of experiments. And at the same time, I also, there is no error bars, but so these two are the scattering lengths that we predicted for the lithium system. For the lithium 6, I mean lithium ion plus lithium atom 6 and 7, and error bars, they are not visible here, but they are here somewhere around, like they are of the size of one characteristic length scale for lithium 6, and they are much larger for the lithium 7 because we are already in the very large scattering length regime. So of course the uncertainty should be rather compared not to the absolute value of the scattering length, but rather to the uncertainty of the phase, and then it corresponds to several characteristic length scale of the uncertainty. But still, we have the error bar that should at least indicate that the scattering length should be really large and positive for the lithium 7, and we hope to confirm it in the future in the experiment. So to sum up, I presented theoretical description of the ytterbium ion plus lithium atom. I presented the first experimental results from the group of René Geritsma for this system, confirming the correctness of our theoretical predictions and giving the new challenges for the ab initio calculation community. And finally, I presented the new proposal from the group of Tilman Pfau for using the Rydberg molecules to really go directly into the ultracold regime of the ion atom scattering. Thank you very much for attention.
Not much time left, but maybe a short question, if any. Yes.
In the ytterbium calculations, how many active electrons do you include?
Excuse me?
In the ytterbium calculations,
Yes.
how many active electrons?
So finally, it was only 2 valence electrons, so only s electrons. So this is no F electrons. So I was able to include F electrons, but without including the excited state orbitals. So somehow, but this is a bit artificial because the excited state that contain F excitation, they are surrounded by the excitation of. So it's like including of 2 of them was not possible. But yeah, we hope that by collaborating with some groups that are maybe developing this kind of methods at the edge. So most probably it can be enough if we can include maybe only the static correlation. So if we can use the methods that can really deal with the highly multi-reference nature, because probably included both of them will be not possible.
So how high excited states would you use? I mean, maybe there's an experiment or plan to use
For
how high? I mean,
but in which experiment?
I'll get this one probably.
Yes, no. So they check excited states, but they plan to use the ion in the ground state. So the applications, I mean, will be to investigate, I think, dynamics. So one of the reasons for this experiment was this proposal of quantum simulations of of the bound structure of fermionic atoms around the chain of lithium of ytterbium ions. So this is the plan, I think, to go into this direction.
Yeah, but you talk about excited.
Yes. So but yeah. So these are the measurement was done only for this free excited state. So this was like to have control, because of course the laser are used to for the preparation and control of the ions. So to know what kind of losses are induced if we are in that state.
Other questions? So let's thank our speaker again.